Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
In this problem, we're given two concentric but different size loops of current carrying wire, and we're asked to figure out what the direction and magnitude of the current needs to be in the outer wire in order to have a zero net magnetic field at the center of both of the wires. So, what is this looking like? Well, let's have a small inner wire. Let's make it actually a little bit bigger. A smaller inner wire here. And we're asked to calculate things relative to the inner circle. So let's just pick a random direction for current. We'll pick the direction that's conventionally positive, which is counterclockwise. So we'll have a loop with a current going counterclockwise here. Right? Then we have another concentric loop that's bigger around this, and we need to then figure out, this is, we'll say, inner loop current. What is the outer loop current? And then what is the direction, right? So is it clockwise or counterclockwise? We're not sure. So we need to figure that out such that we want to have, right, at the center here, ultimately, a net magnetic field of zero. So how do we figure this out? Well, we need to figure out if we need the outer loop to cancel the outer current loop to cancel the magnetic field from the inner current loop. Well, let's figure out what the magnetic field from the inner current loop would be and what direction it would be given the direction the magnetic field would be at the center of the inner loop given the direction the current we've defined for that inner loop. Okay, so by definition, a magnetic field from just a one loop of wire, or actually any coil, circular coil of wire, the magnetic field at the center of that circular coil is given by N, the number of loops in that coil, times mu naught, times the current through that coil, divided by 2 times R, which is the radius, so how far away we are from the center of the loop to the outside of the loop. Now, for the inner loop, the magnetic field at the center of the inner loop is going to be given by the number of turns in the inner loop, multiplied by mu naught, multiply the current in the inner loop, divided by 2 times the radius of the inner loop. Okay, so we have an expression for what the magnetic field would be. Well, what is the magnitude of the magnetic field? What is the direction of this magnetic field? We follow the right-hand rule. We use our fingers to curve around the direction of the current, and we have our thumb that's going to point in the direction of the resulting magnetic field, and in this case, that is going to be out. So the magnetic field from the inner coil of wire is definitely going to be directed outward at the center here. So what is the overall vector of the magnetic field at the center of the inner loop? Well, it's going to have a magnitude of the expression that I have listed here, and it is going to be going out of the screen. So we know that we need to cancel out this inner magnetic field by using the magnetic field created by the outer loop of coil, the outer loop in this diagram. So what is the expression going to be for the outer loop? So let's see what will be right here. Well, we need the number of turns the outer loop has, mu naught. We need to know the current in the outer loop, and then we need to know how big the outer loop is, right? Okay, so we have the expression for the magnitude. So we know these magnitudes here have to be equal if they're able to add up and cancel each other out. But also, not only do they need to be equal, they need to be opposite in direction. So we have to have the magnetic field from the outer loop being into the screen. And what current direction do we need for that to happen? So if we want the direction of the magnetic field from the outer loop to be into the screen, we can put our thumb pointing down, take our thumb, point it down into the screen, and then rotate our fingers around, follow our wrist around, and we'll see that the current needs to go in a clockwise direction, so opposite of what we chose, in order to cause this particular type of magnetic field. So I can get rid of that. Perfect. So that's going to be the direction that we need to have, the current needs to be going in the opposite, and the outer loop needs to be going in the opposite direction as the inner loop. Cool, cool, cool. So we figured out that part of the problem. We have to be going into the screen. The magnetic field must be going into the screen, and therefore the outer loop current has to be going the opposite direction as the inner loop current. Now we need to figure out what that outer loop current needs to be in order to create such a magnetic field that cancels, so that these two magnetic fields created by each of these loops cancels at the center. So that means that the magnitudes of these magnetic fields have to be equal. So we're going to say the magnitude of the inner loop magnetic field must be equal to the magnitude of the outer loop magnetic field. And when we do that, what do we get? Okay, so we have the number of turns in the inner loop times mu naught times the current in the inner loop divided by twice the radius of the inner loop. And that must be equal to the number of turns in the outer loop multiplied by mu naught times the current in the outer loop divided by 2 times the radius of the outer loop. We'll see we have a few things cancel across this inequality. Our mu naughts can cancel and our 2's can cancel. And then we can solve for the current that we want to find because we know the dimensions of each of the loops and we know the current in the inner coil. So what does this look like? Let's rearrange for I out. And what we get is a nice little equation with some particular cool ratios. So the current in the outer loop ends up being equal to the ratio of the number of turns of the inner loop to the outer loop multiplied by the ratio of the radii of the outer loop to the inner loop, and then multiply that by the current in the inner loop. So we plug all this stuff in. We have 140 turns in the inner loop, 180 turns in the outer loop. We have a radius of 0.023 meters in the outer loop, 0.015 meters in the inner loop, and the inner loop has a current of 7.2 amps. So in the end, overall, what does the outer loop current need to be in order to create a magnetic field at the center that cancels with the magnetic field created by the inner loop? Well, that current ends up being about 8.6 amps. And remember, that current needs to be going in the direction opposite to the current in the inner loop in order to create a magnetic field that cancels with the magnetic field from the inner loop. So we have the answer of 8.6 amps for the magnitude and opposite the direction of the inner loop current for the direction.